All right, with that, shall we get started? Good. I'm actually glad most of you made it. I was a bit afraid that since the time is different or like day of the week is different, that some of you will miss this. I think this would be a particularly exciting one. At least I had a lot of fun making this lecture last night at 4 a.m. So we'll see what it's like. Okay. So first thing first, you always start, and this will be true for now on. Well, today, including 4 more sessions, including today. You start by going to the repository for your Python course, and then you do git pull upstream master to pull the latest changes. I already done it, so for my case, there's nothing showing up, but you should see a lot of changes. There's a lot of new files added, including a new notebook. And let me know if you run into like a screen that shows up with some message on, then somehow now you have to get out of it. That's Vim. I have yet to make the video I talked about on how to minimally be able to handle Vim, mostly in the terms of how to get out as soon as possible. So I'll try to have a quick video about it because that's actually a fairly common issue people run into with terminal. But for most cases, git pull upstream master should do just fine. Okay. And once you're past that stage, then go ahead, start a Jupyter lab in the folder. If you have any issues, let me know. Alright, so if you run Jupyter lab, obviously it brings you up to the screen. I'm actually in the different place as usual. That's from usual, so you move up. So if you go up the regular folder as usual, then you should find the 05 Neuroanalysis with Python notebook. Go ahead and click and open it. As always, it's decently long, so it might take some time to load. So let it sit and load, and then we'll get started with it, okay? Let me put this as a full screen. Alright, so this is finally the second half of the course, and this is where I get to cover the neuroanalysis part of the course title of the Edgar's Guide to Python and Neuroanalysis. Now before I dive into it, one thing I did want to clarify is that this is not going to be a full-fledged neuroanalysis course in the sense I'm not really going to get to cover all the theories and math behind a lot of things. Like that is a course on its own, if not a couple courses on its own. And as much as I like teaching those things, and I'll be obviously happy to run a session like that in the future, this is completely outside the scope of this workshop series. So the focus here is more so to see what is it like to be using Python with the packages you already learned, including NumPy, Matplotlib, and a couple others to come, to be using them in scientific computation with some focus on neuroanalysis because, well, we're neuroscientists after all, or a good majority of us in this room. So that being said, that's not so much I'm going to cover a lot of things that's really detailed neuroanalysis. I'm just going to use neuroscience as a good example to motivate the problems and how to deal with some of the data. And I'm not really going to get to step into the theories and analysis and all the caveats if you were to really do this for your own data. Okay, so that's something I want to just get it out of the way. But that being said, this is where it gets fun, right? So far you have just been learning the Python as a language, learn some features about it. We tried a couple things, somewhat realistic problems, but more or less more of an exercise-based problems. When we cover NumPy and Matplotlib, you got to learn a lot about the features of Matplotlib and NumPy, but not really in the sense of applying it to anything that's concrete. And real power of this obviously comes when you actually start applying to something that matters to you, which will hopefully be something like analyzing data from neuroscience. So with that in mind, let's get started. And as it would probably be the case for the rest of the course, we always start by importing some of the essential libraries. These are basically packages that you know we're going to always use, so you might as well just go ahead and import at the very beginning of the notebook. So here we're importing NumPy as NP following the convention. And remember from last time when we covered the Matplotlib, we get to import the pyplot subpackage and name it PLT following the convention doing import matplotlib.pyplot as PLT. And finally, to make sure all the figure shows up inside the notebook, we also run this run this Jupyter magic that starts with percent matplotlib inline. Okay, so just run the whole thing. Okay, so when you start working with real data, and what I mean by real data in neuroscience, it could be quite a variety of things, right? Like that's actually one thing that's interesting but also difficult about neuroscience is that we don't necessarily have one in a common data format, or we don't necessarily even talk about one and the same thing. Some people do electrophysiology recording from neurons, so they actually look at something like traces of membrane potentials. Maybe you deal with spikes, whereas others actually work with imaging data under multiphoton imaging or a scanning microscope that gives you more or less an image to work with, or images to work with, whereas others actually work more with something you record outside of it. Maybe it's the gene expression level, or it could really be any one of those things you can measure about neuron in the brain, or in fact animal. So this variety of the kinds of the data you deal with definitely makes this feel very exciting, but at the same time makes it pretty difficult to have one and concluding course about how to work with neuro data. So rather than me trying to prescribe, okay, this is how you work with neuro data, because there's no such a thing, I'm going to try to visit a couple of different options and take the common things you encounter when you try to work with the data. Now, I've already been kind of stepping into this question of the data because when you work with the analysis, the very first question that should cross your mind is, how do I work with the data? Namely, how do I load the data into my Python environment? So here's, basically you can read this. Of course, I'm not going to quite step through per se. Essentially, when you work with the neuroscience data, it's quite in contrast to what we've been dealing. So in the past, when we work in NumPy, you actually work with data that's generated by yourself as a programmer. You generate a NumPy array or list where you fill the content, or the best case scenario, you use something like input to prompt the user, which is most likely still you, for data. But more likely than not, you actually want to work with data that's generated completely elsewhere, such as your recording system for electrophysiology, or maybe your microscope itself generates data, or any one of those other techniques that ends up giving you some sort of data, typically in a file format. So given this, one of the things you should be asking is, how do I load these data files? And depending on your setup, it could be quite proprietary data file formats. A lot of the microscopes tends to give you one of those. Same thing goes with EPHIS data, electrophysiology recording data. It could really vary from one setup to next across different labs in terms of what is the final file format you're dealing with. So we'll step through a couple of examples, as I said. And the very first and the simplest you can work with is, something like a simple textual files. So here in the data folder, I prepared a couple example data files. And the first thing first, let's actually work with mouse.dat. So if you actually click on it, it will open up the file. You can see the content. So here it looks like it's nothing but a listing of couple, m followed by numbers. So one thing about data file format tends to be like, unless someone that gave you the data tells you what this data is about, you often are lost as to what this really represents. So here, just to supplement that portion, say this is a listing of different mice in the lab, and each of these entries is nothing but the mice name or mouse ID that we use in the lab, hypothetically, right? Okay, so if you were to view this inside the Jupyter, you can actually use this magic called load. So actually, I know I didn't run it. So if you replace this with load and then path to the files, in this case, we're doing data/mouse to indicate that this is inside the data folder, mouse.dat. If you run this, it will load the content of the file and show it inside the cell. So this way you don't actually have to go open it separately. This way you can get the content in front of you. Could be sometimes convenient. Okay, so here obviously there's nothing different. This is exactly what we saw if you were to have a separate tab open for the data file. Now the question is, how do we get this into Python? If you're opening up a file in Python, well, there's actually a convenient function called open, which lets you get a handle of a file object. So let's look at what that means, right? So when you want to open a file, all you do is say open and specify again the path to the file, and it returns a file handle object. So here I just got the F, the file handle object. If you kind of look at it, there's really not much to look at. It is basically some sort of an object that represents a file, but in itself doesn't give you immediately back the content of the file. It has some fancy name along with it. At least it points you to the fact that this is opening this data mouse dat. And in mode R, this means it's in the read-only mode. That's the default. And something about textual encoding, not something to be too concerned about at this point. So you can actually read the entire content of the file by calling the method read on the file object you just got. So here I just loaded the entire content, and if you look at the content, this is what I get. Now notice that it does seem to contain the content of the file and that there are different nice names listed, but with this weird thing \n sandwiched in between every name. Now if you actually print this content, you actually get something interesting in that they somehow print all of these in separate line, and you actually don't see \n anymore. This is because \n is a special kind of character, one of those series of things called escape sequences that is used to indicate special actions. For example, like enter key on your keyboard, which will actually create a line break. By putting \n, you can get a line break inside your string. So because in the mouse.dat every entry was separated by a line break, that is read in as a \n to indicate the fact it was a line break inside the text. Okay, so we already read the content once. What happens if you just read it again? I'm storing it in a separate variable. You actually don't get anything back anymore because once you read the file and you reach the end of it, there's nothing more to read on. So once you open the file and read it once, it takes you, it's like a pointer that exists that starts at the beginning of the file when you just open it, and when you read it, it just zips through the whole file, goes towards the very end, and next time you call read, it tries to read from where it is right now. There are different ways to manipulate this pointer. There's a way to reset it, but more often than not, all you usually do is simply open up a file, read the content, and close the file, and not necessarily read the file multiple times. That's more typical of an action. So I mentioned opening. There's always closing to it. This is actually fairly important. It's actually very easy to slip by. If you open up a file and keep it open, it actually takes some computer resource away. And if you keep on doing and accumulating, you can actually start to make your computer kind of suffer from the fact there are many open pointers to the same file, and occasionally run into issues of multiple things still trying to open the same file. So it's usually always a good idea to close the file handle as soon as possible. Here we already read the content, so let's go ahead and close it. Once you close it, and if you try to do any operations on the close file ID or close file handler, it will issue an error saying this has already been closed. Okay, so here's a bit of a tangent. I may not step so much into it, but it's something for you to read if you want to learn more. I already mentioned this escape sequence, the \n. So by using \n, you can write a single string that actually has things like line breaks or other special characters like tabs. So \n would be a line break if I get a message. With the \n, if I just show the content of the variable itself, it just shows you the \n. The power of these control sequences only comes about when you try to print them. That's when they actually interpret these special control sequences and act accordingly. So if it encounters \n inside print, well, it will make a line break, nicely showing them in a separate line. Here I'm actually showing an example where I use tab, the tab key, which actually puts it in specified, which actually tries to start at the specified position, and I mixed it with the \n. Obviously the problem with this is now it's a bit harder to read it, but you get a nicely formatted string like this when you print it. So you can imagine you might be able to use \t for tab when you want to print something like a tabular data. All right, and one caveat or one interesting thing is that \n, despite the fact that you take two keystrokes, is actually representing a single character. And you can tell by the fact that, well, if I take a variable that contains just plain ABC, and if you print out the length, obviously there are 3 characters in it. But if you also print a variable that has a\nc, which looks like 4 characters or 4 keystrokes it took to type, it still has length of 3. So \n is not 2 separate characters. That's really a control sequence to represent one special character that stands for line break. Okay, and just one more quick thing is that basically If you want to use something like double quotes or single quotes or any other character that has usually a special meaning inside your string, you can use backslash to escape it. That's where actually escape comes from. Basically, get away from the special meaning they usually carry. So for example, if you want to use quotes and double quotes inside a string, well, you can actually try to use double quotes inside a single quoted string variable or single quote and double quoted string variable like this. But what if you want to use both in a single variable, a single string? Well, you can actually just escape the one that would otherwise been interpreted as a special meaning. So if you don't escape the quotes here, your string will actually end up ending there with some weird thing sitting in the middle with another string coming on. By putting backslash, you're telling this is not meant to be an end of a string. I'm just trying to express the character quote itself. And hence, you actually get both double quote and single quote in a single line. All right, so that was enough for tangent. So, okay, so far we actually looked at how to open up a file and read the entire content in. Although this works, it's not necessarily always the most convenient way to deal with the data. Well, since it's a separate lines inside the file, it will actually be far more useful if you could just visit one line at a time. Well, it turns out the file handle object you open implements the iterable. Remember the iterable meaning that you can actually use for loop to step through. And here, if you were to step through an iterable file, what it does is that it steps through one line at a time. So here I'm opening the mouse.dat file again. And this time I'm actually using a for loop to iterate through the content of the file, printing whatever iterates over, which turns out to be single line at a time. Now notice that when I print it, I somehow get empty lines in between each entry. This is happening because each of these still has the backslash n at the very end. All right, so you actually, if you think about it, M122 has a backslash n. So when you just print that, it prints this and then goes to the next line. And now on a separate line, you're printing yet another element. Hence, you get this empty lines in between. So when things like this happens, you often want to strip away the unnecessary and unneeded white space characters, or the white space character referring to anything that's like space, tabs, as well as new line or these backslash n characters. And you can do so by calling the strip method on the string. So an improved version of this is I open up a file, I still iterate through, but as I go through every line, I strip away any of the beginning and trailing white spaces. And this time, because I get rid of those backslash n's, everything prints on this separate line right after each other. So things like this, when you deal with just opening up a plain text and loading out the content, you actually have to deal already with these potential annoyances of like extra characters sitting in, extra spaces and tabs and new lines that you have to deal with. Now, of course, we don't have to print it. If you actually want to deal with it, we often want to put this somewhere so you can continue to work with it. So perhaps what you can do is create a new list, and as you iterate through it, append the data into the list, but making sure to strip because we don't necessarily want those backslash n's. So here you can get, now this is the list version corresponding to the entire content of the mouse.dat. Now it turns out that a file actually comes with a couple of nice methods that you can actually already use to almost get exactly what we just did. And one of those methods that you might be curious to know will be something like readlines. Now, just as a general thing, as I suggested last time as well, it's like whenever you encounter a new function or new method, it's always a good idea to take at least a quick look at the documentation on it, and you can get to it just by putting question mark right at the end. So if you do f.readlines question mark, you can get documentation on it. It's actually pretty short. And you can tell that it basically says it returns a list of lines from the stream, where stream is their way of saying file. Oftentimes in programming lingo, we refer to things like files or even network sources as stream of data or stream of characters that comes in. All in all, if you encounter the word stream, oftentimes it's just fine to think mostly in terms of files or at least source of data that you can read from sequentially. Okay, so with that enough, let's just use this. So I open up a file again, and this time instead I just do the read lines and put the results in mouse list. So I get them separated into lists, but notice that it read each line, including the backslash and the new line character. So it's not perfectly what I want. I don't really care about this \n. And notice it's not on every single one of them. It's actually only present on the 4 because the very last line did not have a line break trailing it. So what we could do, of course, is use a for loop and create another list and just go through each of the elements, strip it, and put in the list. That could be a very typical workflow. But whenever you want to create a new list based on content of another list with mostly one element corresponding to another, but some changes made to it, Python, this comes up so often in Python, and I introduced you a bit last time. It comes up so often in Python that you can use something called list comprehension to do it all in usually one line. So here I'm using list comprehension, which has a syntax of some evaluation for whatever you're visiting inside a list, and put it all in bracket. So here basically m.strip for m in mouse list means that m is going to step through all the content of the mouse list, and for every element I strip it, and I just take a sequence of that, make it a new list out of it. End result, if I run this, I get a list who has gone through and visited every element running strip on it. I actually have a separate file called extra01 list comprehension, which covers list comprehension in much more detail. This is something I strongly recommend that you take a look at it. It's something I didn't feel like it's necessary for us to go in detail inside the course session, but something that I provided you as a resource, and I'll continue to do so with some of the extra notebooks coming up. All right, so that was already a lot just looking at what looks like otherwise exceedingly simple file with just one line of text, one line at a time. Well, that's not obviously going to be everything you want to work with. So here I realized that I didn't strip away these loadings. So here what I meant to show is that, well, sometimes you want to also work with another text that has values separated by comma. Whenever you have things like this, these actually have a fairly conventional name called comma separated values, typically end with file extension .csv for comma separated values. If you have maybe encountered this file in the context of something like spreadsheets, because they actually can output your spreadsheet, like Excel spreadsheet, in formats like CSV, which actually allows you to open outside of Excel spreadsheets. Anyway, so here what I had is in the data, there's another file. Oops, let me go back. File called position.csv. And if you try to open it, the thing is it's a bit different from conventional CSV, so this Jupyter interface wouldn't quite show it. So all I want to show is like if you just go ahead and load it. So here again, let me just demonstrate it. If you do %load and then path to the file you're trying to look at, so load data / position.csv, and if you run it, it loads the content of the data, and you can see it's nothing but a bunch of floating point numbers separated with comma. Okay? And here, this might be, I could say, okay, this is actually recording from me tracking the animal's movement in some position. Maybe if there's a linear track and I'm tracking the position of the mouse movement relative to the end of the linear track. Okay, so same deal. We just open up the file, and let's just go ahead and read the whole thing and store it somewhere. And which is precisely what I do. So I open up the file, and I just got the whole thing. The problem is I did actually just get the whole thing, a long list with all the values stored with comma inside. Obviously, this is not that useful. I want to have individual values, and especially as numbers, so I can work with them. Well, so essentially what you want to do is you want to split this long string into individual components, breaking them or splitting them at comma. Well, that's precisely what split method on the string is for. If you take the data and call split, passing in the character you want to use to split it by, it will happily split it and put it in a list. So here if you do this, it's going to be a fairly long list. At least it has now separated them at the comma position. But notice it's still a string, right? Basically you got a bunch of a list of strings, which is still not that easy to work with. So next thing you want to do is you want to convert each of these strings into, say, floats. Remember, if you convert this into int, it will truncate it. It will forcibly convert into integer. And since many of these are sub-decimals, it probably all becomes 0. So you don't want to convert into int. You want to convert them into floats. So again, we could do another for loop where we visit through each element, create another list, and then append it. or just use list comprehension. Here I'm visiting every value in the split data and running float v, converting them to float, and at the end, like ultimately storing everything in the list. Again, this is just a straightforward use of list comprehension. Following this, now you finally get a list of floating point numbers as you desired. And as I will step more into this, it's actually always a good idea that as soon as you get some data, mostly numerical data, but as soon as you get some data, you try to visualize them. So here, let's actually just go ahead visualize this by plotting it. So make sure, like say I told you that this is a sequence of positions. Well, if it's a sequence of data, it just makes sense to just plot it. So if you plot it, this is say what you get. So this seems to suggest, okay, like maybe the mouse or whatever the animal was moving back and forth on the linear track. So already started to give you some sense of what the movement is. It's obviously real data, meaning it's noisy, right? It doesn't look like a perfect sinusoid, but it was pretty close, right? It's moving a lot. The fact that it's jitter, maybe the animal moved exceedingly fast, or more likely a problem with the recording system or just noise introduced in the recording system, which is also a very commonplace in real-world data. All right, so one thing though, quickly, is that I've actually made use of plot in slightly different fashion from what I've shown last time. Namely, I passed in a list instead of NumPy array, and only passed in a single list, not X and Y points. So what really happened is that, first of all, plot actually is happy to work with list. In fact, it's happy to work with any iterable. It doesn't actually quite care if it's NumPy array or if it's actually a list or in fact any other iterables. As long as it can step through it, it will be happy to just go one at a time and plot the corresponding data point. Secondly, it usually expects X comma Y for you to be able to plot the XY position. So it expects two lists or two iterables, but if you only pass one, it will assume that you're passing in the Y value, and it will just generate an X value that is the index, or the counting up of the data points, where the first data point, the first Y value occurs at index 0, second one at 1, so on and so forth, until the very last element in the list you passed in. So here notice that it's starting at 0, going all the way up to 100, because that's how many elements you have. Okay, so far we actually looked at like loading of the text file ourselves, reading one line at a time, doing necessary fixes in the case of trailing near lines, or CSV where we actually loaded the CSV and then separated on our own. But it gets really cumbersome, and you can imagine as the file gets more complicated, that's a lot of work. That's the very nitty-gritty like line parsing you have to do on a file. And if you don't be careful about this, this could easily eat up a lot of time of you. So to the point that actually I do want to say this, that most times working with the data analysis actually involves a lot of overhead of just getting data into your environment. So to the point that loading data could be as much as 50% or even 80% of what ultimately constitutes your time spent working with the data. Obviously, this is not a good thing. It's not an ideal situation. But something to be aware that loading data and parsing it to the point you can finally work with it could actually take a lot of work. Hence, whenever you save data, or whenever you actually think about how should data be saved and how it should be organized, it matters a lot, because if you don't be careful about it, you'll be doing a lot of what's called data parsing, where you're just trying to go through your files, get the content out just so you can start analyzing it. That being said, there are this is like age-old issues, so for many common data file formats, solution has already been provided for you with good implementations on how to deal with it. So for example, if you actually have NumPy, which we all do, it actually comes with some nice functions that let you load in directly from CSV, and you could be pretty smart about it. So one of the ones you want to be aware of is NumPy's load text, or load txt, it stands for text, function. And it's actually pretty good about understanding how to load file formats like CSV. You just have to be a bit specific about it. So if you look at the documentation, it's fairly comprehensive. It actually tells you different options associated with it. So obviously the first one is the file name. It needs to know which file is it that you want to try to load from. It may ask you for data type. So if you actually think if you know that this is not going to be numbers you're loading in, you could tell them so it can understand these data files correctly. It also has other arguments like delimiters, skip rows. There are many options, and if you're curious, it's something you can read through the documentation to find out exactly what it means. Here, one of the key is the delimiter. This is basically saying, how do I know, or what character do I use to split different values in? So in this case, since we know it's a comma-separated value, your delimiter should be comma. So let me just collapse this. So here I'm using the load.txt function, load text function, to load instead of having written our own open file thing. I pass in the path, the data position.csv, and make sure you pass in delimiter equals comma. This tells the load text that this is how you split data up into individual elements. And doing so immediately gives you a list of values, the floating point values that we took some time to actually get to in the previous couple of steps. Now what's nice is that it could also know to deal with a bit more complicated CSV files. So before we actually run it, this one, let's go ahead and look at the data. And I prepared this one called block_data CSV, which actually looks a bit more like typical CSV file. So you have different columns, indicates what that data column is about, and each row is, say, an entry from an animal. So you have different values that, even with the description given at the column, it's still not quite obvious what this is really about. This is not the point of this exercise, but it's also to show you that these data alone could actually be a bit hard to understand what this is about. So this goes on the topic of what does it mean to actually make your data available, which is something we'll actually go a bit further in next week. But here at least you get something, and it looks like, aside from the first row, it looks like it's a bunch of numbers. Now one thing that's always interesting to do is, like, if you right click on it and open with and use editor instead, it will just show you as a plain file. And here you can see that this is basically the first line. I think the red is coming out of something else. The first line is just separate a comma separate value of the column heading, and then from second line on is where the actual data begins. So you can imagine if you were to do the file parsing yourself, open up the file, read one line at a time, you have to actually know to skip the first line because that's not what the data is. That's actually just a label of your data. So things like that could easily get very cumbersome, and it might be hard for you to deal with all the file quirks about it. And that's why, if possible, you do want to work with something that has already been implemented for such files and just learn to use them well so you don't have to do all the hard work. So in this case, in a long story short, you just want to use NumPy load text. And on top of the delimiter comma, which is still what you delimit or separate entries by, you're also adding this another optional keyword argument, skip rows equals 1, to indicate you want to skip the first row because that's not what contains the data. So you can run it, and you actually get the number data out of this. You can go ahead and see what happens if you omit skip rows or just go with the default of 0. It will complain because at the very beginning it reads the first line and then takes a string, and because it tries to make a floating NumPy array, it tries to convert into float, and names like start position quite doesn't translate into float. Okay, so let me put it back. But oh no, if it's entirely numbers, it seems to work just fine. The issue arises, of course, if you have something that's even more complicated and has many different data types in it. So here now I have a name data.csv. If you look at it, not only does it have the data we had, but you'll have an extra column which indicates the name of the subject. It's obviously in string. So if you were to try to load this using NumPy load text, even with the delimiter of, even with the skip rows of 1, which will get rid of the heading, you still have textual information, and you will have issues dealing with it. So whenever it comes to working with CSV or data format that actually can have multiple kinds of data types in it, it might not be as straightforward as just using something like NumPy to try to load it. And you might actually have to turn yourself to more table-oriented packages in Python. And one good example of that would be something called pandas. It's a package that is very table-oriented. It has far richer capability in terms of loading stuff that looks like table. So for this course, I'm not going to step into the details of pandas. It's something that after this course, I'm pretty confident that you can read up on your own and start to learn how to use it. But just to show what it might be useful for, you import pandas, convention is to import it as PD. And pandas comes with a lot of reading methods just like NumPy, but a bit smarter about tabular data. So here, if you just read the CSV, and notice that you don't even have to tell them that you have to skip rows and comma separated. I mean, it's read CSV, it knows it's comma separated. It also knows how to smartly deal with the first row being the label of the columns. So now said, if you just load it, you actually now get a very nice looking table inside your Python because pandas actually understand tabular data much better. And in fact, it has a lot of features, like you can actually address by column using names to get just the content of the column. And you can do slicing just like you can do on NumPy to extract, say, specific rows out of it. So it's a pretty nice extension on top of NumPy, especially when you're working with data that's tabular and therefore can have a lot of different types of the data. So something to keep in mind. All right, so we took some time to understand how to work with textual data and comma-separated values. So the first one where there's like data per line, so oftentimes that's actually referred to as line-separated values or new line-separated value. And the one in which we actually now have even additional commas to separate distinct values, that's obviously the comma-separated values data format. And it typically corresponds to 1D array-like data content and 2D array data content, respectively. But what if you actually want to store something much more complicated? And we already dealt with and seen arrays that goes 3D or even higher. How can you express that in a inside a file format? Now, obviously, you probably don't want to write it on your own, right? Like you can maybe imagine, okay, maybe I'll have yet another delimiter, maybe a semicolon to indicate different like super rows. Like the first dimensions are separated by semicolons, next one is separated by commas, and ultimately new line separates the very zeroth axis. So you can start coming out conventions like that, and it could easily get out of hands. Well, fortunately, NumPy comes with its own way of saving these files or these data into a file format. And in fact, it doesn't use textual data. What it does is it converts your numbers into binary, so just zeros and ones to make sure as it's compact as possible, and put in a file in such a way that preserves information like the shape of an array, and also, of course, store the content of it. So let's take a quick look at it. Here I'm creating just a random 4D array with some shape I decided randomly, so 10, 5, 3, 4, and I just create some data. If you look at it, you're going to be shown a lot of data content in it filled with just random numbers. And say I want to save this. Maybe this means something special, or maybe I just want to save it for reference. Well, fortunately, NumPy comes with this save method. So as again, or save function, sorry. As again, you always want to look at the function's docstring, at least quickly. And here you look at it, it's actually, well, not too long. Basically, it says, okay, when you call save, you pass in the file name into which you want to save, and array that you actually want to save into that file. Okay, that seems straightforward enough. So what you can do now is that you can do save data, and I call it random 4D, and I'm storing my data, the random array I just created. If I run this, and I realized like I actually committed this with you guys, but if you run this, you actually get your random 4D array. By default, it has .mpy extensions added to indicate this is a NumPy data format. And while I don't necessarily recommend you guys all do it, so you can just see me do it, if I try to open it, yes, it doesn't quite understand it because it's actually a bunch of zeros and ones and doesn't really have a specific textual information. It just has a binary data that represents an array when loaded by NumPy. Okay, so fair. Not worry too much about exactly how it looks like in the file. What's important is that it contains the data. So we saved it. Now we want to actually load it. And just like you probably could guess, the counterpart of the save would be the load function. And this time, since you're just loading data that already exists as a file, you just specify the name of the file, and it gives you back a NumPy array. So I'm storing that as the loaded data variable. And I mean, I could look at it. More informative would be something like just looking at its shape. 10.5.3.4, which is consistent with what I saved. And just to verify this loaded data is the same in terms of content as my original data, I can do comparison. So if you remember, if I do two array comparison, it actually does position by position comparison. So by default, it will create another array of same size filled with trues and falses. Here I'm interested in if every value is true, meaning that every value corresponding position are the same. And I can do that by saying NP all, which will take a Boolean array and checks if every one of those entries are true and returns true only if every one of them are true. So here by doing this, I get true, meaning that yes, it is indeed same exact value at every single position. Now just to show the fact that this loaded data is a separate copy, right? It's not so much that you save the data from the memory per se. You just save the content and now you're loading it as a separate copy of NumPy array, meaning that if now I change the data and say fill it entirely with 0, but if I look at the loaded data, it still preserves the same content that you loaded. So the moment you save and load, you don't actually have any linkage between the two array that was saved versus loaded. They just becomes a copy of each other. They have a different life. Okay, so the bottom line is when you actually have NumPy array data or something that is easily expressible as NumPy array, this NPY or NumPy file format is actually a very, very convenient way to save and also load from. Potentially to the point that if you actually have an option, you probably want to save your data in this format and share with others. Of course, with the understanding that it has to be open using NumPy package. But given the NumPy is so ubiquitous, at least among the Python users, this is a very conventional and useful file formats that among Python scientific community, they actually prefer to use something like this when it comes to sharing data. Now, before I move on and actually start looking at some more real, actual thing that we can analyze, since so far we've only been talking about loading data and really haven't done any analysis on it. One thing I do want to mention, oops, I just jumped around. All right, there it goes. Is the fact that I so far been only talking about loading textual files, like with the open, and reading it. I really haven't taught you how to do write to a text file, like writing your own CSV. And the reason I don't cover this, despite the fact if you pretty much open any Python textbook, they will always cover these two in pair. The reason I don't cover it is because I don't think you should really be doing it, at least not as your default method. Oftentimes you're concerned with loading data that came from external sources, as I said, recording systems, and many times they might be provided to you in some form of text formats. Maybe it was some sort of survey which is done and put in an Excel spreadsheet and then ultimately saved in CSV that you now have to load. So not only is it that when it comes to loading, you definitely want to use some functionalities or function that already exists to make your life easier, especially when it comes to saving. You should almost always use one of those functions rather than writing your own way of putting down data line by line in text files. So it's for this reason that I don't quite cover writing data into textual file yourself. Obviously, Python has all the features, and ultimately speaking, all these things that actually writes to a file, all the functionality provided by any package to write to a file, does use Python's writing capability. I don't think it's something that you should think of as one of the more common things that you should be doing when working with data in Python. That being said, to make it complete, and for those cases where this is still useful, I will have an extra notebook that covers the topic of how to write data. And not only textual data, but also cover in there how to read and write binary data. So it will be coming up. I obviously haven't added yet, but that's something I'll provide as an extra notebook. But I'll stand by what I said, that it's not something that's commonly done. And if you make me count the number of times I had to use the writing to file capability over the past 3 years of, say, intensive Python work, probably twice. Okay? And that's with me working with packages that actually specifically deal with writing a library for people to use to work with data. So that's even outside the context of my usual day-to-day research. In that context, maybe I use that function twice or use that capability twice. So that should at least give you an idea of that, how uncommon it actually ought to be to just write text file line at a time. Okay. All right, so we at least learned how to load NumPy files. And I told you how this is a very convenient way to share data. But we actually now look into loading some of the interesting data I provided you in the form of NumPy files. So here's a sample neuronal trace that you can load, and it's provided in this neurotrace.mpy under the data folder. So I'm just going to load it. I'm going to call it activity because I already give you information. This is some sort of neuronal activity, say electrical activity. So I load it. Now you can do this, and sometimes you don't want to do this. Maybe you just want to look at the content of the NumPy array you just loaded. So okay, that wasn't too catastrophic. Sometimes if it's really big, it's just going to end up filling your entire screen if you did it. Often to the point that before you look at the content, it's usually safer to, I should already have it there. It's usually safer to just go ahead and check the shape. So here it actually contains 83,455 entries. So you definitely wouldn't have wanted to print it like vertically. That would have actually just scrolled through the entire notebook and would be quite annoying. At least if you have a 1D array like this, or if it actually goes too big, NumPy actually does save you from that trouble and just gives you a truncated list. So here it basically shows the first tree and last tree values and ... in between to show that, hey, this is longer than what I'm just showing here. And because oftentimes if it goes above anything like 10, I mean obviously it depends on your memory capacity perhaps, but for me if anything goes above 10, I really cannot grasp by just looking at the NumPy file. Like I'm not going to suddenly start to be able to picture what exactly it looks like. Definitely not just by looking at the numbers. So that's where visualization actually comes into play. And this is, if there's one thing you take away from me covering all of this, aside from the file loading, is that when you get your data, or maybe someone else's data, or when you just get data that you're about to analyze, I suggest that one of the very first things you try is to visualize it. Like look at the data. And by when I say look at the data, I don't mean as in like look at individual numbers. That's usually not that helpful. You actually want to do some sort of plotting on it so you get a visual interpretation of what this data looks like. This is also often one of the best ways to catch anything weird about the data. It's so easy for you to write a function that processes your data and computes something and never ever actually look at the data, despite the fact that if you would have looked at it, maybe you would have immediately detected the fact there's something wrong with it. So in general, I strongly recommend that when you get a new data, take a look at it. So this is what exactly we do. Since this is a neuronal activity, it's a sequence of electric activity measured over time. It just makes sense to just go ahead and plot it. So if I plot it, this is what I get. So for those of you who are already like somewhat familiar with the electrical raw traces, you might feel that, okay, this looks like spiking data. Basically, this is like a membrane potential of a neuron that you record, say with a single electrode, and after a while, it seems to be somehow spiking, as in like has an action potential that fires. That's what this sharp peak looks like. So I will say this is like an activity, a membrane activity of a spiking neuron. And given this is just a NumPy array, you can actually look at small segments of it just by slicing and replotting it. Right? So here I just randomly decide I'm going to slice at the 45,000th position, looking at the next 1,000 data points, and I plot that, and I get a bit of a zoomed-in picture of it. And here it does indeed look like something that could be considered like action potential. It has the rise and a bit of refractory period, the dip in the membrane potential. Now, obviously, this is not like a picture-perfect action potential you may have come to expect out of textbooks. Like those are much more of a cleaned-up view of what this could be. In real life, all your data tends to be very noisy. So you see, like when it's not firing, there's a lot of activity, like a lot of this jitter that still goes on. This is the noise, right? And as I said, as I indicate, half the battle of like working with data could be about loading your data. Another 20% or more of your data analysis battle tends to be dealing with noise. How do you smartly deal with noise to extract the interesting phenomenon you're chasing after? Okay, so notice that I plotted this, and there are a lot of data points. Obviously, since I only passed a NumPy, right? Yeah?
What is the x-axis?
Yes, good question, and that was exactly what I'm talking about. So yeah, so x-axis here, because I only give one NumPy array, is simply showing the sample count, right? So here it goes up to around 80,000 because there are about 80,000 data points. So obviously this is not that informative. You actually would like to know what the x-axis actually correspond to. And this again goes into this idea of just because someone gave you data doesn't mean you have a complete picture of it. You actually here have to know what each sample means. So here, because say I'm the producer of the data, I come by and tell you like, oh, this was just like electrical activity measured and sample at 32 kilohertz. Okay, what does that mean? That means that every sample of electrical activity occurs at 1 out of 30, well, I don't know what a better way to say is that I measure 32,000 samples per second. Okay, so with that knowledge, what you can do is convert the sample number into time. And the way you could do this, first of all, let's just prepare an array that goes from the 0 to the sample number. So again, this could just be done by a range with the length of activity going in. And if you now divide this by the sampling frequency, hertz means 1 over second. So if you now divide it by, it gives you the position in time for each sample. So that's what I get the sample time. And finally, with the sample time, I can plot the activity against the time to actually now have a bit better understanding of what the x-axis is, here given in seconds. So now with this knowledge, we know this was actually recording done over about 2.5 seconds. So a pretty short segment, right? You might have been initially thinking like this seems like a long one because you have 80,000 data points. Or if you're sampling at 32 kilohertz, that's barely 2.5 seconds of recording. Okay, so we actually now finally loaded some interesting looking data, and we even went ahead and visualized to get some idea. So namely, if you were to look at this, you can at least tell that first half seems to be fairly quiet, as in there's no spike going on, and in the second half there seems to be some spiking activity going on. If you're an experimenter, maybe this suggests that you've actually presented some sort of stimulus. Or maybe you change something about the settings so that now the neuron starts firing. Or maybe this just simply corresponds to the fact you turn on the switch so you're actually finally getting actual recording. It could be any one of these variables. Obviously, just looking at data wouldn't quite tell you. So again, this is another stressing point that just because you have a raw recording doesn't quite give you a full picture of what your recording was about. All the associated information such as sampling frequency, measurement of the y-axis. So here I actually kind of secretly just went ahead and said this was millivolts. But if I didn't tell you that this was in millivolts, you probably wouldn't know. Maybe I did some weird scaling. Maybe you had to scale it to be able to get to the millivolts. So things like that occurs all the time. So just because you get a data that you can load doesn't mean you have a full understanding of your data. And this is again something that I'll stress and probably try to cover a bit more in detail next week in the last session of the course, which is about organizing your data. Okay, that being said, let's actually do something interesting. So far, all we've done is just loaded data and looked at it. Well, that's not quite an analysis. At least no one's going to quite approve you for being a good data analyzer if that's all you do. Visualization is key. It's the very first thing you should do. But let's do some analysis so we can show that we know how to work with the data. One of the very, very common things to do when you just get a data in is to compute a couple statistics. By statistics, I mean some aggregation information you can extract from the data, which could be anything like mean, standard deviation, or maximum, or median. Any one of those things, these are all called statistic. And by computing it, you have computed a statistic for the data. They could give you some sense of, say, on average, how big the data, how was the activity? How much does the data spread? Did it vary a lot? Or like maybe if there's outliers, you can compare mean against median to get a sense of how mean is shifted so much away from the median. But there are many, many things you can look at it and get a sense of just by looking at statistics. So oftentimes it's a good idea to quickly compute and try to get some sense. So as you already know, NumPy comes with a lot of functionalities to compute some of the basics and most commonly used statistics, such as mean, standard deviation, and median. Almost all of them available as functions, so you can just go ahead, run the statistics on the NumPy array. And for some selected few that are very, very common, they are even available as methods on the NumPy array itself. So here I can do activity.mean, activity.standard deviation. Obviously, it should be identical as the one above. Okay, so looking at statistics is interesting. Also, another typically good thing to do if you're talking about statistics is to actually look at the actual distribution of the data. Oftentimes, you could actually be fooled just by looking at mean and standard deviation, because in your mind, you might be thinking that looks something like a normal distribution, a Gaussian distribution with a bell curve. Okay, many data does have that property, but many data also don't. So if you think of mean standard deviation as like, well, there probably is like a lump at the mean, and standard deviation is just some measure of the mean, some measure of the spread. Well, if there actually was data was really composed of two bumps, like you could be completely fooled and you could completely misassume something about your data. So part of your looking at data should also be about, say, plotting the distribution. When it comes to distribution plotting, you plot something called histogram. Hopefully you know what it is. Basically, it's just a way to express bin values of the, say, y-axis. You just count how many times does that value occur. Overall, it just gives you an idea of the spread of your data or the distribution of your data. So here, we can do histogram just by doing plt.hist. It's something provided by the matplotlib. And here I'm using the fig to actually generate a figure object on which things will be plotted. And I'm using the fact that if I use figure, I can specify something like resolution, which is the DPI. So anyway, if you just do it, you get a histogram. The problem here is that it uses very few bins by default, so it looks like it doesn't really look like anything. You can tell that there's a peak occurring somewhere around negative 75 millivolts. But I mean, with two bars, it's really hard to tell what's really going on. So this is where you get to control the behavior of the plotting function hist by passing in an argument bins. So if you say bins equal 100, it now uses 100 bins to try to express the distribution, giving you a much finer view of the data. So here, if you look at it, okay, indeed the data does look like a normal or bell curve distribution. So if you were to do any analysis or any test that assumes that your data is a bell curve, this may not be a terrible data to work with that assumption. But always get a sense of your distribution. As I alluded to, many statistical tests like sample t-test, z-test, or ANOVA, all the things that you'll probably come to because you have to get the precious p-value for your experiment, assume something about your data. Please don't go through statistical tests until you find some test that gives you p-value less than 0.05. That's not how statistics works. Statistics works under assumptions. They assume something about your data, and under the assumption can tell you whether this really has a value, say, that's bigger than this or not. So if the assumption is not true, and most of the time the assumption is your data looks like a normal distribution, if the assumption is not true, you cannot use that test. If you use that test to test your data, you will get a wrong result. It might give you false positive or false negative. And ultimately, you could be publishing something that is not a true statement. So just trying to get understanding of your data, it's critical to understand what the distribution looks like. So it's a good idea to make a habit that when you visualize the data, just do one quick histogram. Look at the distribution so at least you can tell whether it looks like, say, a normal distribution or not. And that's already a very good start when it comes to the time we have to start doing statistical tests on it. Okay, so that's with me being obviously very passionate about people misusing statistical tests. Yes? Which one? Oh, yeah. So this is just basically showing the last thing you've done with the plot. So this shows like if you actually did the X label, this is like where did they put the X label on? Yeah, so this actually happens a lot with the plotting. This actually doesn't make it into the plotting, especially say when you save the plot, this doesn't get in there. This is just printing what's returned by the last statement you run. If you want to suppress any one of those statements, if you put semicolon at the end, it actually happily suppresses it. But oftentimes, since it doesn't really matter, you can just leave it as is. But good point. Okay, so one thing we noticed when we were looking at the raw data, so if you just scroll above, you guys don't have to do, but when I scroll above and look at the raw, just the data, there is a bit of difference between, say, first half of the recording and second half of the recording. There's a lot going on much more in the second half, and not so much going on the first half. So we actually just ran statistics on the entire recording, but we already know that it probably will be a bit different in terms of how data are distributed from first half to second half. So given scenarios like this, and this is thanks to the fact we looked at the data, we can actually be a bit more informed about statistics by saying, like, what if I look at statistics for the first half versus second half? So in order to do that, you can simply use the fact that you can slice an array to the point wherever you want, and just let's split it into first half and second half and run statistics on it. So to be able to get the first, like the center point, basically the sample that corresponds roughly to the half point, what I'm just doing here is I take the length of the activity, which gives you total number of samples I have, and I divide it by 2. But notice I use divide 2. This is because if you take any number and divide it by 2, and say if it happens to be an odd integer, it will give you something dot 0.5. Here I'm interested more in the position, like actual index. So if you know you just want to truncate it to the nearest integer, you can actually use integer division, which is // to make sure what's returned is an nearest integer. It rounds it off, actually. So if I take half point, length of activity // 2, I get an integer that corresponds roughly to the half point. And I say roughly because if you think about it, if you have odd number of data points, it's impossible to split it into 2 equal half. So this gives you just sum of that one. You could have easily taken the half point and add 1 in the case it was odd to change which one has 1 extra data point. Oftentimes you don't care. And one nice property of length integer divided by 2 is that if it's integer, this will give you the correct position to split it up. Okay? So here basically 41,727 is the position that you should split it at. So I'm going to take, starting at 0, if I'm ignore it, it defaults starting at 0. I'm taking a slice from 0 up to, but not including the half point index. Call it first half. And I'm taking another slide that starts at half point and goes all the way to the end because I'm not specifying the ending value. So this is a very quick way to split your data into 2 halves. And again, whenever you manipulate your data, always try to look at it. Even if it's a very simple operation, that one plot you generate just to quickly verify cannot hurt. So here I'm just making sure, okay, this is what the first half looks like, and this is what the second half looks like. Notice that I've generated new t values just to give you more time-based value that corresponds to the number of the data points. So I just took the total number of data points, created an A range, so it goes from 0 to the number of data points. And because I know the sampling frequency is 32 kilohertz divided by 32,000 to get the corresponding seconds. So here this first half corresponds to about 1.4, maybe 1.3 seconds of recording. And second half is the other 1.3 seconds of recording for a total of about 2.5, 2.6 that we started out with. Okay, so this seems to correctly capture the split we were interested in. Let's now just do statistics on it. Because I want to actually do statistics like mean, standard deviation, and median, just print them out, rather than me typing in multiple times, I felt like, okay, this is probably where you could write a function that if you were to pass in data, just spits this out, print them out so you can just get exactly to the thing without having to me type the 3 things for every segment I'm working with. So I quickly defined this new function called print_stats. I just came up with the name, which takes the data. It expects it's a NumPy array. You can tell it expects a NumPy array because it calls something like mean, standard deviation on it. And then just prints it. It doesn't return anything. It just prints these values. So armed with this function, I basically say, okay, for the first half, and I print the statistics. Just to make it easy, I just print some separation line, and then I print the statistics for the second half, giving me something like this. So it's visually easy to appreciate the difference between the 2 segments. There's no confusion which value corresponds to which half. So looking at it, what statistic seems to be the most different? Does mean look quite different between the 2? Not really, right? Median also doesn't look that different. Only one that's significantly different between the 2 is the standard deviation, which is a measure of the spread. If you look again at your data, that should kind of make sense actually, right? So here notice that because I plotted separately, they use different scale. Here this is just plotting from -50 to 90, -90-ish. That corresponds to just this tiny segment, obviously. But the second half actually has spikes, which causes it to vary quite a bit. So it only makes sense that it has a higher value of standard deviation. So when it comes to data analysis, things like this where you just take something, and even if it's just verifying your intuition, it's always a good idea to just try it and comparing against the data, visualize it, see if it always makes sense. These tiny steps can mean a lot, especially when it comes later on when you're trying to finally summarize it into a manuscript. Okay, so that's where I'm going to end just neural activity analysis. I actually later on have a whole segment that talks about, okay, if you were to have a spike like this, oftentimes what you want to do is actually detect when the spike occurs. And that's a very typical electrophysiology analysis process called spike detection. Spike detection is an art on its own. It has a lot of research into it. There are many, many different complicated and various algorithms developed to perform spike detection dealing with various kinds of noise and situations. So it's not something you just want to quickly come up and start using for your recording data. It's something you want to research into to see what's one of the latest and most well-tested algorithm and try to use that, and hopefully it's implemented already as some sort of library, say in Python, that you can import and use so you don't have to do it from scratch. So that's usually what you ought to try to do, but it really doesn't hurt to know in principle how these things tend to work. So that's where I actually basically towards the very end of the notebook go through what if I was to implement my spike detection, what would it look like? What are some of the concepts I can apply, like thresholding, detecting the position of the when it crossed the threshold. All these things are there. It's just that it does go into a bit of a detail, and I don't necessarily feel like that's something that's in the best interest of you, and especially doesn't apply to every single one of you. So I keep it in there for your viewing pleasure, more or less. But it does have to give you some information. It also gives you good usage of something like the fancy Boolean indexing. How could it be used, say, to detect spikes? So if you have time, I by all means recommend taking a look at it. If it's not something that you will work with on a day-to-day basis in terms of electrophysiology, obviously don't worry too much about the details, but it could be a good example on how something like complicated, how something as complicated sounding as spike detection could actually be implemented in just a few lines of code. Again, don't take this algorithm and start applying it to your data. If you did that, I'll be very shocked and very sorry for it, right? Like that, this is not by all means it's not even a good algorithm. It's very crude. In many ways, I can already point out issues with it, but it's definitely a start. And I can happily say at least the complex spike detection algorithms that I work with on a day-to-day basis is, in principle, not that different. It's just that it has a lot more tricks and minute details that makes it extra good. Okay? If this is something that you're really passionate or just want to know about, I'll be more than happy to talk about it, but outside the context of this course. Okay, so let's change gears a bit and look at characterization of neuronal responses. One of the very typical thing you'll be doing research would be to say, understand how neuron responds to stimulus. So far, we only look at recording. I haven't even told you what the recording was about. I haven't told you, was it from the V1, the visual cortex? Was it from the auditory cortex? Or was it just like hippocampus or wherever it was, right? Obviously, those things matters because oftentimes you're looking at responses of neurons to some manipulation outside, or at least some controlled condition under which you're trying to study the properties of the neurons. This is a very typical way of approaching electrophysiology-based experiments. Or it doesn't even have to be electrophysiology. Maybe you're working with fMRI and you're looking at the both signals. Both signals also do correlate with what you show or what you present to the subject. In that case, it could even be humans, obviously. So oftentimes you are interested in the brain's response to the outside world and specifically manipulations you perform in the outside world, which often manifests in this form of stimulus you present. So with long story short, let's talk about visual cortex because that's what I work with and I feel like it's the coolest system in the world. I'm totally fine if you disagree with it. We can agree to disagree. So with the visual cortex, the primary visual cortex in mouse specifically, I'm looking at the responses of visual cortex to different images, say of raccoon, because they probably encounter raccoon once and sometimes, right? and at different contrast. Maybe what I'm interested in is like, well, if they were to see a raccoon at very low contrast, say as in like super foggy day in dark versus right under the sun in super sharp contrast, what happens in the brain? Are there raccoon neurons in V1? Are there something that correlates with contrast? Maybe I'm more interested in contrast, right? So here I'm presented, same image presented under 5 contrasts, starting from 0%, which you obviously cannot see anything, going up to 100%, which is the sharpest I can present, at least for this particular image. And I'm interested in seeing, okay, do neurons respond differently to different contrasts? So what I've given you is this hypothetical experimental recording of a neuron from V1 responding to different contrast values. So let's just go ahead and load it. Done, I've already loaded. If you look at it, it's a bit hard to see, but it actually is 2 by some array. It's a 2D array. And again, as I keep on stressing, it's usually just better to look at the shape first. It is a 2 by 55 array. And as an experimenter, I'm telling you, oh, the 2 numbers, the 2 rows correspond to contrast and then neuron's response. Here measured as firing rates. So here I'm already assuming that I already recorded from the brain and I have already performed spike detection. So I actually counted the number of spikes and divided by the total number of the data segment to give you a firing rate and use that as a measure of the brain's activity. This prescribes obviously to this particular way of thinking about the brain called firing rate coding. You could easily think of any other ways of coding, but fairly typical way to think that when brain is interested about something or neurons interested about something, it tends to fire more. At least that's how we define neurons' interest. There are many other ways of coding, and this is also kind of something I closely work with. Again, if you're really interested, I'll be more than happy to talk about it, not in the context of this course. Okay, so with that said, I told you already that first row is the contrast, second row is the firing rate. Okay, fine, let's just extract it and look at it. Again, visualize. So I take the first row. Remember, you can take if it's 2D array, if I just index by one number, it corresponds to different rows. Remember, in Python, it starts at 0. So first row is index 0. I get here I'm storing as x. And then second row, I'm storing as y. And I'm just quickly plotting. And since I know x is contrast and y is firing rate, I do make sure I label it. And okay, this is what I get. What just happened? Why does it look like this mess? Does this mean somehow, is this like informative of this mess? No, not really. And the reason it looks like this mess is because it treated your data as if it's a sequence of data, where sequence matters. And as an experimenter, I could tell like, well, actually sequence doesn't matter because that 55 corresponds to 55 trials, where on each trial I just randomly pick a contrast and show to the mouse. So whether like that particular trial will occur at 10th position or 30th position or any other position doesn't really matter. What really matters is individual data points. Whenever you encounter data where sequence itself is not important, you rather use something like scatter plot rather than a plot, which is a sequential plot, to be able to actually visualize the data. So here I'm also doing a bit better discipline where I actually take the data and store on the variable that's a bit more meaningful rather than x and y's. So I call it contrast and firing rates. And now I plot it using scatter plot. Okay, this looks a bit better. Now you actually can at least see something about your data. And in fact, you can already see some interesting things about the data. So here you can see, looking at just the different contrasts, I seem to be presenting 0% contrast, 10% contrast, 30%. Looks like I'm doing in increments of 10%. And if you really closely look at the data, you notice that I actually give 5 values, so 5 repetition of the same contrast. And this is something you can obviously verify with the experimenter, or if you're the experimenter, it should go other way around. You know your protocol. If you look at the data, it better correspond to what you thought you did. I cannot tell you how many times this actually saved me from having continue on with the wrongly designed experiment. You assume you've designed your experiment correctly. Please verify the assumption. You're at the closest point of just being able to verify. So just quickly visualize the data. Make sure it exactly matches your expectation. If you thought you presented from 0 to 100, showing 5 repetitions of 10% increment contrast, your data better reflect it. So here okay, that looks correct. And I'm seeing the firing rates does vary across contrast. And if I squint an eye enough, I can see it actually kind of increases with contrast. Fairly actually typical for visual cortex. There are many reports on this phenomenon of contrast modulation. Basically, if you increase the contrast, neurons in visual cortex tends to fire more. Okay, so that's good. That seems to be there. And in fact, if you look at it, it looks like just a straight line, sort of, right? Whenever you encounter data points that appears to be related around a straight line or linearly related, well, it's usually a good idea to do some analysis that shows that relationship, namely one being a very popular analysis of linear regression. Okay, so now I'm, of course, diving into the topic of linear regression. And when it comes to linear regression, I do have a couple things to say. Linear regression actually, or analysis like linear regression actually falls into category of analysis that I will actually group as model fitting. And this is not necessarily how everyone or every textbook describes what linear regression is. Especially if you study linear regression under the course such as statistics, or at least like introductory statistic, they might just present it as a thing you do to the data, thing you can quickly check, but not necessarily formulate it as a model fitting. Now, what do I really mean when I say model fitting? Model fitting means that when you have two data, say contrast and firing rates, you're trying to explain one of them from another. You're trying to predict how is it that one of the variables, say firing rates, arise from contrast. Can I use contrast to explain the changes in the firing rates? Oftentimes this comes about when you're interested in explaining how is it or what is it that the neuron is responding to. So here I'm interested in saying firing rates respond to contrast. But the question, of course, becomes, okay, well, how? And what is the exact relationship between contrast and firing rates? Can I describe it? By trying to give a more precise mathematical description of it, maybe you get a better insight into the process that causes, or at least like that's related to this relationship that you actually observe in your data. Long story short, basically, whenever you actually doing something like linear regression, you're trying to say, okay, I assume this is how the relationship is, and you're trying to be as close as possible by tweaking some of the parameters, some of the things you can change about your model to be as good of a description as possible of the data you just observed. So here, basically, I believe that there's an underlying line, like as I increase contrast, firing rate tends to increase. And I believe it's somewhat linear, meaning that every 10% contrast increase, maybe I see about 3 or so increase in firing rate. Now, obviously, this is not perfect. If it was perfect, this should be a perfectly straight line, and there should be almost no question that this is linearly related. What is challenging, but also at the same time makes this interesting, is the fact that it's very noisy. All your data from here on ever is always going to be noisy. And I can very safely say so. If you encounter non-noisy data in your experiment, you probably have a bug, right? If you're really recording from something, noise is going to be there. And obviously, this could be a manifestation of limitation of your recording apparatus, or it could just be a reflection of the fact that there's more complexity to life in the brain than your simple assumptions. Noise itself can mean a lot. It could be basically, we use the term noise to basically refer to anything that we can't quite explain, but that doesn't necessarily mean it's just a bug or it's just like something you can always remove. That very thing you call noise could actually be a reflection of something very deep and interesting going on in the brain, or in fact, for that matter, any data you ever record. So with that, introduction about noise, basically what I'm saying is that I believe that the firing rate is some slope times contrast plus an intercept, basically a line that we all learned from our algebra course. Okay, as I said, obviously this cannot be true. This definitely cannot be true because it doesn't look like a perfect straight line. So there's something missing. Well, the missing portion is the noise. Basically, my refined model is that, okay, I believe the firing rate is slope times contrast plus an intercept plus some noise. this choice of plus, like adding a noise, is my modeling choice. I could have basically said maybe it's multiplied by noise. Maybe the noise could be squaring this thing. You can come up with whatever form, but whatever the choice you come up with, that is your model of the data, and any analysis and fitting you perform is based on that model. When it comes to linear regression, what I just described, the firing rate is slow times contrast plus intercept plus noise, is precisely what's assumed under linear regression analysis that you encounter in pretty much any textbook. Now, not only that, specifically they assume something about the noise. They actually assume that your noise is distributed like a normal distribution with a bell curve. So meaning, if you were to just take the noise component and look at the histogram across many trials, it should have a shape that looks roughly like this, centered at 0. The fact it's centered at 0 makes this an unbiased noise, meaning that noise alone wouldn't really shift you one way or another, but it is a Gaussian or normally distributed noise. So this is another one of those things that something as harmless appearing like linear regression is already laden with a lot of assumptions. So if you perform a linear regression, keep in mind that this is the model that's going in. You're saying that there's a slope, there's an intercept, and you're assuming your noise looks like a normal distribution. Okay, so with that enough background and hammering of the linear regression, let's actually try to do a linear regression of the data. I'm going to show you two ways. One is pretty much probably the way you will actually be doing linear regression, and if you actually look at any one of us actually doing linear regression, this is how we actually do it, which is to use a implementation of linear regression already provided for you by some package. Namely, we're going to look at this package called SciPy. It stands for Scientific Python Packages. It's one of those very popular scientific Python packages, very redundant in that way, just like NumPy and Matplotlib, but it's really a collection of many functions related to doing scientific computations. And one of the things it comes with is a statistics sub-package. So it's basically, if you think of package being a folder, sub-package is a folder inside a folder, which then contains a lot of Python code or Python files. That's precisely what statistics sub-package is. It's a folder with a lot of functions inside many Python files that is aimed at giving you a lot of capabilities to perform statistical analysis, with one of the functions being linear regression. Another way we're going to look at is, well, if you didn't have access to things like this, or if you're just curious, or maybe you just want to see and do the actual analysis yourself, you can actually implement linear regression from the definition using the math. And there we're going to take a look at how we can do this with the NumPy. Okay, so SciPy, as I already referred to, SciPy is a big collection of many scientific Python-related functions. If it actually had quite a few packages, so unlike NumPy and Matplotlib, where each of them were pretty specific in terms of what is they're trying to provide you, with NumPy providing you a numerical array that you can work with, and Matplotlib obviously about plotting. SciPy actually is not, it's hard to really describe SciPy under one heading because it's really a collection of many things. So if you were to visit their website, and if you, here I'm actually linked you to the introduction, you can see that it contains many sub-packages, and at least there are about 10 or so sub-packages, some of them saying cluster, which is about clustering algorithms, FFT for this thing called fast Fourier analysis, integrate for integration and ordinary differential equations, so on and so forth. So there are many collections, and each of them have hundreds, if not thousands, of functions inside for you to be able to use for that specific topic. So it's not a terrible idea to familiarize yourself with topics or the general category of sub-packages in SciPy, such that if down the line of working with Python you ever encounter need for oh, I need to do some signal detection analysis, then if you would have known that, oh, there's a signal package, there's a chance they might contain something useful for me. That's the level I would suggest you keep your knowledge about SciPy at. Just have a rough sense of what packages it might have, and just make a habit of whenever you encounter sub-special topic in scientific analysis, try to check with SciPy to see if they already have a package and a bunch of functions pertaining to it, because it could save you a lot of time. Okay, so one of them being stats, which is statistical distributions and functions, so very generic, but one of them is a linear regression function. So, to do that, to use that, what you do is you actually import the sub package from SciPy, and since I want to just be able to easily refer to it, I renamed the imported sub package under stats. So I do import scipy.stats as stats. If I don't do this as stats part, every time you want to use this package, you have to keep on saying scipy.stats. That's too much typing for me, so I'm going to say stats. Okay, so and stats alone comes with a lot of functions. So one thing you can do, and this is something you should try, and one actually functionality of the Jupyter Notebook I haven't really been mentioning, but you really should using, is that whenever you say you want to look at the content of a package, you can do dot, and if you do tab, it will actually give you a listing of all the things that can follow that dot. Meaning this is usually all the functions that can be found in the package. So I mean, again, like this is not something you want to memorize or anything, but this actually also could be sometimes a good way to see what are available. And if you were to like say type partial names like lin, for maybe you're thinking like, oh, could there be linear regression? Just by typing lin, and if I do tab, it will actually do the auto completion. If there are many that matches something that starts with lin, then it gives you more narrowed down version of the list to do the completion with. So this is also very helpful. And using tab completion can actually save you a lot of typing mistakes. So here there's a lin regress function for linear regression. And again, you want to look at the doc string at the very beginning before you start using it. Okay, so if I look at the doc string, this is, again, not too long. Actually, it's complete with examples for how to use as well. So maybe you can take a very quick look at it. It says calculate linear least square regression. That's a full name for linear regression analysis for two sets of measurements, x and y. Okay, so I mean, it makes sense. Basically, it would do a linear regression line fit on your x and y data. And the interesting part is what it returns. It returns slope, an intercept, but it also returns three more things. R value, this is the correlation coefficient. This is a statistical measure of how linear your data is. This could go anywhere from -1 to 1. -1 means it's perfectly negatively correlated, so it means a downgoing slope. 1 means perfectly positively correlated linearly. Perfectly positively linearly correlated. And 0 means they are not linearly correlated. But be aware that 0 linear correlation doesn't mean those two data are not related. In fact, if you say have a relationship that looks like a quadratic function, basically like like curve up, if you try to fit linear regression, it will often give you a 0 correlation coefficient, depending on the data you end up getting. But again, that doesn't mean that those two variables are not related. In fact, they're very strongly related, just not linearly. Again, this is the reason I keep on stressing this is a model fitting. You're proposing that they might be linearly related, and by performing linear regression, you're testing the model by fitting to the data. And after you fit the data, you must test how good the data fit is. All right? Okay, and then there are other things like p-value. This tells you basically the p-value that you're probably familiar with in terms of the null hypothesis that the slope is 0. So this basically suggests like, okay, once I fit it, is it the case that it has any slope relationship? So this actually, this comes up once in a while. P-value that's not significant still come about for completely linearly related in some sense if the slope of the linear relationship is 0, which is often interpreted as no relationship whatsoever between the two data points because changing the x-axis doesn't change the y-axis. But it might be the case if you plot it, it looks like a perfect line. It's just completely flat. So there you would say that, okay, it's still linear relationship in some way, just not in a meaningful one because now you cannot use the x-axis value to make any prediction about changes in y. Okay? So anyway, that's the linear relationships. And standard error is just like given the standard error of the greatest estimated gradient. Yeah, so this is just saying like, oh, what is the measurements like your confidence basically on the slope that's estimated. These are obviously something that if you really want to understand what these values means, you have to study up a bit more in the linear regression, something I'm not going to step into for this course. But these are very common values that people seek when they actually do linear regression, so they return it for you. And just to give a quick idea, say here they just randomly generated x and y's, and this is how they use it. So basically they say stats, linear regress, pass the 2 values in, and you get 5 values back. So doing the expansion assignment to get the 5 values assigned to 5 different variables, and then they'll take a look at it. Okay, so with that, we can go ahead and do that ourselves. I'm passing into the stats linear regression my contrast as the x value and firing rates as the y value because I want to predict the firing rates from contrast. And again, this returns 5 things: slope, intercept, R value, correlation value, and the standard error. We're not going to really look at the last 3 values, but since it returns 5 things, you have to catch it somehow. So here I do it, I run it, it's done. It's very quick. And we can just look at some of the values. So slope, okay, it gives me 0.145, and intercept is 2.4667. The values in themselves may not be the most enlightening, right? Like you might not be able to like say whether this really makes too much sense or not. At least for slope, this is obviously how much the firing rate increases per one increment of 1 change in contrast. So earlier, let's just quickly look. Earlier I was saying like, okay, maybe for increase of 10, I get change of, I was guessing something like 2-ish. So that means for change of 1, I expect something like 0.2 change. So the fact I got a slope of 0.1456 doesn't seem too off. I didn't really think too much about intercept, so I don't really have too much comment, right? And you can also look at these 3 values here, and just for the sake of it, I'm giving you. Here at least you can look at the p-value, and you can see p-values as small as you probably could ever dream of. Now you can actually get quite a bit smaller value than this, but here at least the p-value is really, really small, of 1e negative 13, so that's far less than 0.05 that you might seek after whenever you do statistical tests. So this suggests that, yeah, your slope is definitely not 0. Or at least it's quite significant, statistically significant difference in slope from 0. That's the correct way to say it. It would be completely incorrect for me to say the difference is significant. The significance of result is not what statistical tests for. What it tests for is that is it statistically significantly different or not, without telling you whether your result is significant or, in other words, impressive or not. So don't ever confuse those 2 things. All right, so I got a slope and I got an intercept. That's my model. Again, remember my model was slope times contrast plus intercept, and in reality, noise. But if I exclude the noise, you can treat that as my expectation. Basically, without any other thing, since noise is a random factor, if I had to give my best guess of what the firing rate would be, it would just be slope times contrast plus an intercept. That's my baseline expectation. So let's go ahead and plot it. Here I prepare a value of x that goes from 0 to 100. Just randomly have enough data points to make the plot look nice. And I get x times slope plus intercept. So x is contrast, y is the resulting expected value of the firing rate. And if I plot it, okay, I get a line. Obviously that in itself is not that interesting because I kind of knew I was going to get a line. So whenever you have a model that you just fit it, you don't just want to look at it, right? That's not that interesting. In fact, you know the model, so you know what it should kind of look like. If I'm fitting a line, I expect a line. If I'm fitting a sinusoid, it should look like a sinusoid. What's more interesting is, does it fit my data well? So every time you're trying to verify your model, it's a very good idea to plot it against the data that you're trying to describe. So here I'm repeating the plotting. I'm plotting again my line, but along and on top of the scatter plot of the raw data points that went into the fitting. And this is what I get. So looking at it, it's actually quite up to you to decide whether this looks like a reasonable estimate or reasonable depiction of the relationship between the contrast and the firing rate. It doesn't look too terrible. It's definitely noisy, right? Like if I'm saying like for 60, I'm predicting about say 12.5 or so of firing rate, I get quite a bit of variation, right? And maybe this is the best you can do with the contrast. And quite likely for this data, I mean, in fact, I know this data since I generate the data, this is as close as you can get to describing relationship between the firing rate and the contrast. But if you happen to have, say, another variable measured during the experiment, maybe you have a measurement about the eye position of the mouse, or maybe some other information. Maybe if you have this other information, you can explain the rest of the variability. This idea of what can you use to explain away the variability is an essence of model fitting. This goes in hand in hand with the idea of explain variance. In a perfect world, with enough measurements made, you can explain every single deviation of your neuronal response. We're far from it, and there is even some hypothesis suggesting that is in principle impossible because there's inherent noise in the brain. But we know for sure that at this point, say with even visual cortex simply responding to something that looks like a plain grating, like that's something that goes ups and downs, even there, we're far from being able to explain most of the variability in the brain. So there's a lot to be done when it comes to like explaining the brain, how it responds to the outside world. But this is kind of the approach you take. You try to incorporate more factors in to see if you can explain something about the brain better. All right, so again, that's the thing. As I said, this is the model. The expected firing rates plus is equal to contrast times slope plus intercept. Right, that's the baseline model. What I want to do now quickly is to see, okay, my underlying model was that there's this deviation which should be normal distribution. Now I have a model that fit it. I can ask, is the deviation actually normally distributed? This is basically a sanity check. You basically started with the linear regression saying my noise should be normally distributed. I fitted a model now. I can look at now what's noise, the basically deviation, this deviation away from the actual line, and just look at it and then plot it. And if that looks nothing like normal distribution, you probably should reconsider your model.
Did you just first assume your model is?
That is correct, completely correct. Yes, I just first assumed it was normal distribution. So this process of you assume first, you fit it, and then verify is also exceedingly common because oftentimes there's really no way around that. All right, so what you do is basically for each of actual contrast I recorded, I use my slope and intercept to make prediction of the firing rate that I would have expected. So that's my expected firing rates. Since I have 55 data points, this should be, again, 55 values. So you can just quickly verify that's the case. And I compared one-to-one against my actual firing rates, computing the difference. And finally, we already know how to do a distribution plot using histogram. So we just do a histogram on the difference and say this is what I get. So looking at it, this looks reasonably normally distributed. But obviously it depends on who you're going to talk to and how rigorous you want to be. With 55 data points, it's pretty hard to be able to say whether something is exactly normally distributed or not, to the point that you can always argue this is simply impossible to say whether something's exactly normally distributed or not. But here, looking at the data, at least I wouldn't immediately say and start freaking out like this looks nothing like a normal distribution. It looks somewhat like a normal distribution, meaning that your assumption is probably okay. There are different things now you can run even on top of this to say check of Gaussianity, which is something that's checking the normality of your data or the noise. There are additional things you can do to see whether your assumptions seem to hold true or not. Okay? And that obviously just keeps on going in terms of things you can check, right? And it goes into like a lot of like minute stuff you might end up wanting to check. Maybe the better way would have been just to record more data so you can get a better picture of the exact distribution. Stuff like that is something you'll always end up considering as you perform experiments. All right, so then last 10 minutes or so, I just want to very quickly cover, okay, what if I don't want to use a function that's already provided for me? I actually want to do it mathematically on my own. I'm going to very quickly do this section because I don't want to go through the derivation of the math. This is not really the point of the course. And I'm not even really going to take too much time explaining exactly what's going on. So if matrix algebra and vector algebra is not really your thing, and say you don't care for it, don't worry too much about this. I mean, obviously it's in the notebook, so it's for you to take a look at it, and I stand by the correctness of the implementation of it. But I'm not going to really step through to make sure that you understand exactly all the matrix manipulations I'm performing. Okay, that being said, linear regression in matrix notation is written usually like this, where y, which is a vector, a column vector actually, of the y observations you made, is equal to a matrix multiplied by yet another vector. The first matrix X is going to be a matrix that consists of your X values. That's your first column. And second column filled with ones. The filling with ones stands for the fact that you're going to have this constant offset that you're going to try to learn. That stands for the fact that you are going to learn an intercept. You then have W, which is going to be the learned part, the something you're trying to fit. It's the row vector. First number is your slope. Second number is the intercept. Together, this amounts to each y computed as the first column x value multiplied by slope plus 1 multiplied by the intercept, which then sum together, which is exactly the same thing as slope times x plus intercept per y value. So this is how you express a linear relationship. Given this, and if you try to fit under Gaussian assumption or normal assumption about the noise and optimize it, you arrive that the way you compute the W is by computing this complex looking matrix notation. You take x transpose multiplied by x, invert it, and multiply into x transpose, finally multiplying onto y. Okay, again, I'm not going through the derivation at all here. I'm just showing you this is the computation involved to actually get at the slope and intercept. So quickly, I'm going to put my contrast and firing rates and call it x and y because it takes some manipulation. I want it to be short, so I'm going to call it x and y now. I prepare a vector of ones that is as long as x, and I stack it up together with x to create this matrix where first column is x, second column is 1. That's how I get x. You see, this is exactly what I went for. And the shape is, indeed 55 by 2, as I desired. Y is currently a 1D array, but I want it to be a column vector. So we used the trick we learned last time, or last time or the session before that, where we can add an extra dimension by using NP new axis. This makes it from 1D array into 2D array, where there's a singleton dimension on the second axis. All in all, meaning y has a shape of 55 by 1, representing a column vector. Finally, in order to do my calculation, if you look at the math, I should collapse this. If I look at the math, I need to do multiplications, matrix multiplications actually, and inversion. Inverse of a matrix is not a trivial operation. It's not just like divide by the thing. You actually have to do inverse of a matrix. Not something you want to implement. Obviously, you can implement it if you really must. This is such a common operation. Obviously, it's provided by someone. And NumPy has a sub-package called linalg, corresponding for linear algebra operations. And one of the functions that comes there is inv, for inverse of a matrix. So you take the inv, you happily import it, and now I simply do the exact math that is shown here. X transpose multiplied by x, inverse of that multiply x transpose multiplied by y, where every multiplication is a matrix multiplication. So remember that if you want to do it, you don't use the multiply the star symbol because that's an element-wise multiplication in NumPy. If I want a matrix multiplication, I use the at symbol. So it's x dot t for transpose matrix multiplication x, the whole thing inverted, bless you. Matrix multiplies x transpose, matrix multiplies y. That's mouthful to say it. At the end of it, though, it computes W happily. And now you look at the W, as I said, the first value should correspond to your slope, second value to intercept. And I doubt anyone exactly remembers these numbers, but if you look at this and compare to what the SciPy linear regression returned, it's identical. Meaning that this is indeed how they implement a linear regression, and we did it correctly. Okay. So that being said, you'll probably be thinking like, I'll probably never do this myself. I'm just going to use SciPy linear regression, and I agree. That's probably what you should be doing. But there are going to be eventually, once you start working more and more with models, if that's a thing you want to do, you will get to the point where you're coming up with a model that no one has implemented yet. If you, in fact, in the field of research, if you're not doing that, then you might have to start the questioning like, are you actually doing a modeling or just doing some line fitting that someone else provided? If you're doing real modeling work, it's inevitable that one day you have to implement your own model and your own way to fit it. So there, these matrix manipulations and learning the NumPy's way of doing it would become essential. But given that this is not going to be something that applies to everyone, I'm not going to step any further into it. Obviously, something that I'll be happy to talk about, and maybe even have a complete separate course on it. Okay, so as I said, there's an advanced topic, which is like a pretty long description of how to do a spike detection. Very simple method, but at least somewhat enlightening, hopefully. So I leave it like that. I'm not going to step through it because it would take probably another good 40 minutes to step through this. I put as much description as I can do, at least something I can come up at 4 a.m. in the morning. So I hope it's self-explanatory. If some part doesn't make sense, you know how to bother me, how to find me. So do ask me questions on it. And this is where I'm going to leave it for this session. In the next session, what I'm going to cover is additional topic of image analysis. So I know a lot of you work with imaging data. This could be microscopy data. It could be scanning microscope, point microscope, or just like multifocal microscope. So working with image is very typical. And we're going to look at cases of how to load an image, how to visualize an image. We already done a tiny bit of it last time. But we do much more in depth on how to visualize image and how to do some computations on the image and maybe doing some changes to it, like thresholding and such that. Okay, and one more note that I have is about homework. So I hope that you've had a chance to work on the GitHub homework. Obviously, it was meant to be very straightforward. Like you had to just make initial commit followed by one more commit just to show that you know how to do multiple commits and push it to the repository. If you haven't completed and if you are interested in turning in future assignments, please do so. Please complete it because this is how I'll be distributing the next homework assignment. The next homework assignment is going to actually be distributed hopefully by the end of tomorrow because tomorrow's session is at tomorrow. Well, next session is tomorrow at 3 p.m. I'm going to actually, after the class, follow up with a link, just like I posted last time on Slack. If you click on it, it will take you to a repository that contains the description of the homework for you to complete. Most likely, it will look like a couple of notebooks. You go in and follow the instructions and provide your own code to complete, say, the plotting exercise and file loading exercises. But the way you would turn it in is by getting obviously signing up, getting your own repository, cloning, working on it, and pushing the change. And after a week or so, I will probably say in the last week, so a week from tomorrow, I will go ahead and try to take a look at what you have committed at that point and provide some sort of feedback on it. Okay. So I know there's like a very short time between today and tomorrow, but if there's some specific topics you want to cover by an analysis, I'll be happy to go over it. Also, for the sake of making it visually interesting tomorrow, if you have some cool images that you want me to kind of try to analyze, do by all means post it on Slack, and I'll probably randomly pick one and then use as my example cases. Otherwise, it'll probably be an image of a raccoon or frog or something like that. So just, if you want to see something that looks more visually stimulating, provide me with some images, and I'll be more than happy to work with it. All right, and that's all I have for today. So if you just will help me put together the tables, that'll be great.